So, you know how to get from point A to point B. That's usually not the hard part. But what if there are a dozen different ways to do it? How do you find the best one? You know, the cheapest one, the fastest one, the most efficient. Well, there's a search algorithm designed for exactly that. Today, we're diving into uniform cost search.
All right, here's what we're going to cover. First up, why do we even need something more than a basic pathfinder? Then we'll get into the secret sauce of UCS, its cheapest first strategy. We'll walk through an example, prove why it always finds the best path, and then wrap up by talking about its performance and where it kind of hits its limits.
All right, let's jump right in. Look, a lot of search algorithms out there are great at finding a solution, any solution. But the real world is messy, right? Not all paths are equal. Taking the highway might be faster but costs more in tolls. A scenic route takes longer. Every choice has a cost attached to it, whether that's time, money, or just plain distance.
And that's really the core problem we're tackling here. Finding a path? That's the easy part. But how do you find the cheapest one? I mean, the absolute guaranteed lowest cost route possible. That's a whole different ballgame. And it's exactly what uniform cost search is designed for. Okay, to really wrap your head around this, let's put it side by side with an algorithm you probably already know, breadth first search, or BFS. Now, BFS is all about one thing, finding the path with the fewest steps. It's looking for the shallowest goal. UCS, it couldn't care less about how many steps it takes. Its one and only mission is to find the path with the lowest total cost. So a short two-step path that costs 100 is, to UCS, way worse than a long, winding five-step path that only costs 20. It's all about the final bill.
So how does it actually do that? How does this obsession with cost change how it searches? Well, it all comes down to a really simple but super powerful strategy.
And here's the big idea. It's beautifully simple. Uniform cost search always expands the cheapest node first. That's it. It keeps a list of all the places it could go next, the frontier, and at every single step, it looks at that list and asks, which one of these has the lowest total cost to get to from the very beginning? And that's the one it explores.
I love this analogy for picturing how it works. Think about breadth first search. It's like dropping a pebble in a pond. The ripples spread out in perfect, even circles, right? One layer of depth at a time. Well, UCS is totally different. Its ripples spread out based on cost, so you get these weird, wavy contours of equal path cost. This is huge. It means the search might go way down a five-step path before it even touches a two-step path, all because that longer journey is actually cheaper so far.
Okay, that's enough theory. Let's make this real. We're going to walk through a classic example so you can see exactly how this cheapest first thing plays out in practice.
So imagine we're planning a road trip through Romania. We're starting in a city called Sibiu, and we need to get to Bucharest. All those numbers on the map, that's the distance between cities. And for our purposes, distance is cost. The mission is simple. Find the absolute shortest route.
All right, step one. We're at the starting line, Sibiu, which obviously has a cost of 0. From here, we've got two choices. We can drive to Râmnicu Vâlcea for a cost of 80, or head over to Făgăraș for a cost of 99. Now remember the rule, always expand the cheapest node. So what's it going to be? Yep, Râmnicu Vâlcea at a cost of 80 is our next stop.
Okay, so we've expanded Râmnicu Vâlcea. From there, we see we can get to a new city, Pitești. And here's the key thing. We have to calculate the total cost from the very beginning. So that's the 80 it took to get to Râmnicu Vâlcea plus the 97 to get to Pitești, giving us a total of 177. Now let's look at our options, our frontier. We've got Făgăraș sitting there at a cost of 99 and our new path to Pitești at 177. Which one's cheaper? Făgăraș by a long shot. So that's where we go next.
So next up, we expand Făgăraș. And what do you know? From Făgăraș, there's a direct route to our destination, Bucharest. The cost of that leg is 211. So let's add it up. 99 to get to Făgăraș, plus 211 to get to Bucharest, that's a grand total of 310. Awesome! We found a path to the goal.
Now hold on. Most algorithms would just call it a day right here. Goal found, we're done. But not UCS. It looks at the solution, and it keeps going. Now why on earth would it do that? We found a path. What more could there possibly be?
Here's why. Because it knows there are still unexplored paths on its list that are cheaper than the 310 cost solution it just found.
See, Potesti is still sitting on the frontier with a total cost of just 177. Since 177 is less than 310, UCS has to explore it. So it does. And from Potesti, it finds another path to Bucharest. This one has a cost of 101. Let's do the math. 80 plus 97 plus 101. That comes out to 278. Whoa, it just found a second, completely different path to the goal, and it's way, way cheaper than the first one.
That right there, that's the magic of UCS. This incredible ability to find a solution and then say, hold on, I think I can do better, isn't an accident. It's built right into the core logic of the algorithm. And this is what gives us its famous guarantee of optimality.
So what's the trick? It's a subtle but absolutely critical difference in when it checks for the goal. Think about BFS again. The moment it generates a goal node, the second it sees it's a possibility, it shouts, I'm done, and stops. UCS is more patient. It only bothers to check if a node is the goal when it pulls it off the frontier for expansion. And remember, that only happens when that node is the absolute cheapest path found so far. By waiting until that moment, it guarantees that no other, cheaper path could still be lurking out there.
And the secret weapon that makes this all work so elegantly is a special data structure called a priority queue. You can think of it like a VIP line at a club. It's not first in, first out. Instead, every item in the line has a priority. For us, that's the path cost, and the queue always serves up the item with the best priority, which in our case is the lowest cost.
So let's take a quick look inside one. You can see it's just a list of nodes and how much it costs to get to them. We've got a path to node E that costs 9, one to D that costs 3, and one to P that costs 1. The priority queue is smart enough to know, without a doubt, that the path to P is the top priority right now, because it's the cheapest.
But this brings up a really important what-if scenario. What happens if we're exploring some other part of the graph, and we suddenly find a new, better shortcut to a node that's already in the queue? Like, what if we find a cheaper way to get to node E? This is where the priority queue is just brilliant. It doesn't get confused and add a second entry for E. Instead, it just updates the one that's already there. So if it finds this new path to E that only costs 5, it just goes, okay, scratch that 9, the new cost is 5. And then, automatically, it reshuffles its internal list, bumping E up in the priority line. It's this constant, dynamic updating that makes sure the algorithm is always working with the absolute best information it has.
Okay, so UCS gives us a rock-solid guarantee that we'll find the optimal solution. That sounds, well, perfect, right? But you know there's always a catch. With any algorithm, there are trade-offs. So let's talk about performance. So here's the report card. Is it complete, meaning it'll always find a solution if one exists? Yup. Is it optimal? You bet. But then we get to time and space complexity. And yeah, that formula looks a little scary, but don't worry about the exact math. What it's basically telling you is that the performance is tied to how expensive the final solution is. The more costly the optimal path, the more work the algorithm has to do. And that points to its Achilles heel. It can be pretty slow and eat up a ton of memory. Just to quickly demystify those variables for you, C* is just the fancy name for the cost of the best solution, and epsilon is just the smallest possible cost for any single step you can take. So all that formula is saying is that the runtime depends on the ratio between the final answer's cost and the cost of the tiniest steps. If your best path is super expensive and your steps are super cheap, well, UCS might have to explore a truly enormous number of nodes to find it. And that really brings us to the final critical takeaway here. Uniform cost search makes you a promise. It will find the perfect, cheapest path, guaranteed. But that guarantee comes at a price. It might have to explore a huge portion of the search space to get there. And this forces us to ask a really practical question. When is a good enough path that you find really quickly better than the absolute optimal path that could take forever to discover? That's the trade-off you always have to think about when you're deciding if UCS is the right tool for the job.